Hey there and welcome. Today, we're diving deep into the hidden world of civil engineering. We're going to look at what it actually takes to hold up an entire mountain when you decide to, well, punch a hole right through it. This is the story of the invisible engineering behind a massive railway tunnel.
Okay, so let's get right into the heart of the challenge. What you're looking at is a map of the path for a new railway tunnel called Tunnel 7. Now, that big orange line that's soaring up and down, that's the ground level above the tunnel. You can see right away, it's not flat at all, is it? The tunnel has to cut through shallow valleys and then bore deep under these huge mountain peaks. It's a total geological roller coaster.
And this leads us to the million-dollar question for the engineers. It's really the core of the whole project. How in the world do you design one single tunnel that can safely handle all of these wildly different situations? I mean, you can't just copy and paste the design for a shallow part and use it for a section that's deep under a mountain. So, how do they pull it off?
Well, the answer to that entire puzzle, it actually comes down to one single crucial concept: overburden. Let's break down what that really means.
Overburden is just a fancy engineering term for all the rock and soil sitting directly on top of a tunnel. The simplest way to think about it is like the tunnel's own natural roof, just one that's provided by the earth itself. And understanding the weight, the pressure, and the strength of that roof is the absolute master key to designing a safe tunnel underneath it.
So how do you design for the whole thing without modeling every single meter? Well, engineers have a really smart shortcut. They model the two most extreme scenarios they're going to face. By figuring out the absolute highest risk point and the lowest risk point, they can confidently design for everything that falls in between. And here they are, the two models, side by side. Take a look at the diagram on the left. That's minimum overburden. That's our shallow, weak, super high-risk situation. Now look over to the right at maximum overburden. That's the deep, strong, low-risk one. To really get what's going on, let's break down the most dangerous one first. So, let's dive into that high-risk case. This is where the tunnel is really close to the surface, and the rock right above it is weathered and weak. This is the spot where things can get seriously tricky for the engineers. And when we say shallow, we mean really shallow. At its weakest point, the tunnel has just 6 meters of ground above it. That's barely the height of a 2-story house. For a gigantic railway tunnel, that is an incredibly thin layer of natural protection. It's practically nothing.
Let's dig into the details a bit. The computer model identifies this high-risk area as being in highly weathered rock, which is basically rock that's been broken down and weakened over millions of years. This gets confirmed by its RQD, which stands for Rock Quality Designation. Think of it like a report card for the rock's strength, and here it's scoring less than 50%, which is basically a failing grade. All of this just adds up to the weakest spot and the highest risk along the entire tunnel path.
And this is what that risk looks like. See all those red lines spreading out from the tunnel? Those show areas of extreme stress, where that weak rock is literally failing under the pressure. The model predicts what it calls a maximum vertical settlement of 120 millimeters. In plain English, that means the tunnel roof could actually sag by nearly 5 inches. To an engineer, that is a massive, flashing red flag.
So what's the verdict here? It's simple. For this section, a much tougher, heavy-duty support system is absolutely required. You need to build a powerful cage of steel and concrete to basically hold back all that weak, fractured rock and stop it from collapsing into the tunnel.
Okay, so that was the nightmare scenario. Now let's completely flip the script and look at the total opposite, the low-risk section. Here, the tunnel is deep underground, the rock is super strong, and for once, geology is actually on the engineer's side.
And just look at this contrast. Instead of a tiny 6 meters of overburden, here we've got 64 meters. That's more than 10 times the amount of rock pressing down. Now, you might think more weight is a bad thing, right? But in tunneling, it's the opposite. All that weight actually helps hold everything together, creating this immense natural pressure that makes the rock around the tunnel even more stable.
So let's check the stats for this area. This section is made of compact quartzite, which is a very strong, stable type of rock. It scores way above 50% on that quality scale. And here's the critical part. The model found far fewer plastic points. You can think of these as tiny little zones where the rock is starting to bend or fail under all that pressure. With so few of them here, all the signs point to a much lower risk.
And here is the visual proof. See how much cleaner and calmer this model looks compared to the last one? There are way fewer stress points around the top of the tunnel. And the predicted settlement? It's only 41 millimeters, about a third of what we saw in the high-risk scenario. This incredible stability means the engineers can use a much lighter touch. For instance, the rock bolts they need to pin the rock together can be a lot shorter here. So let's put the two solutions right next to each other. In the high-risk zone, you need a heavy-duty approach. Really long rock bolts drilled 4 meters deep into the rock, plus a thick 150-millimeter layer of shotcrete. That's a special concrete that gets sprayed on to form an instant hard shell. But in the low-risk zone, they can use a much lighter touch. Shorter 1-meter bolts and a thinner 100-millimeter layer of shotcrete. It's a perfectly tailored solution for each specific problem. And this is what it all boils down to, the engineer's smart decision. By analyzing these two extremes, they get all the knowledge they need to make choices that are not only safe, but also economical for every single meter of this tunnel.
And this whole process is incredibly systematic. First, they analyze the geotechnical profile, which is basically just creating a super detailed map of all the rock types. Next, they use powerful computer simulations to predict exactly how that rock is going to behave under stress. Then, they monitor those results, looking at key factors like settlement and strength. And only then, as the final step, do they select a support system that is both perfectly safe and cost-effective.
And here's the payoff, a quote taken straight from the engineering report. This process makes the selection of the support system more realistic and economic. It's all about getting maximum safety without wasting time or money. It's like they say, you don't build a fortress where a simple fence will do the job just fine.
So, if there's one key takeaway from all of this, it's this. Great engineering is never one size fits all. It's a precise science of matching the perfect solution to the specific problem you're facing. Every single meter of this tunnel gets exactly the support it needs, no more and certainly no less. And that kind of leaves us with a final thought, doesn't it? At its core, engineering is about predicting and controlling invisible forces, like the incredible stress in rock deep underground. It makes you wonder, what other invisible forces are engineers planning for all around us, in the bridges we cross, the buildings we work in, and the systems we rely on every single day?